we were initial part of the discussions we were doing, and in that we have observed that what is an NPN transistor, why it is called as a transistor, and what is the basic feature that makes it different to that of the diode action, and what are the meaning of the symbol, how we are representing the symbol, that we have discussed. Also, we have found out that the basic principle or the basic functionality of this whole thing is that we have to make sure that we are having a diode like if it is an NPN transistor, if we are looking at an NPN transistor, then based on that, the emitter and base junction, that is this part, emitter and base junction, this should be connected as in a forward bias condition. So this, if you want, this should be something like this. All right, it will be like this, and at this point also we will have something of this nature. So this is how we are supposed to connect for an NPN, because if we are looking at it as in terms of NPN, the majority carrier will be here, the electrons, the negative ions. All right, so whenever it happens, this negative ions will move towards the collector side, keeping in mind that the base region is significantly small, or the concentration of holes are really small, so that most of the current which are generated, or the electrons which are generated from emitter, goes to the collector, and on the opposite way, the current is generated in the opposite direction, as well as the flow of the intensity of the final current will also be improved or increased based on the collector region, which is significantly wider compared to the emitter and the base. And we have also observed the current. Primarily, there are IC, the collector current, the base current, and the emitter current. These three currents are primarily they constitute the whole action. And also we have found out that there is a very simple relationship that actually exists between the, I don't know whether we have done that, but anyway, the very simple expression, simple expression that relates these two, and that is given by IE is equal to IB plus IC. So what does that mean? That the constituent of emitter current is given by a very small little amount of IB current, which is a base current, and a portion of the collector current. So definitely IB should be very small, because the dopant over in the base region is very small. So IB is sufficiently smaller, and IC actually holds true, or IC for the matter of IC, the whole value of IE is calculated. And based on that, we have also discussed. Sorry. What happened? Just give me a minute. Oh, okay, fine. Yeah. So in that aspect, we have also found out the voltages across, and that was given by the VBE, the VCB, as well as the VCE. These are the three specific voltage across the different terminals of the transistor. Now, along with that line, we have also found out that for the device, as I said, if you consider the physical parameters of it, this was a diagram that we had shown you. I was showing you. So if you observe here closely, that we have the collector which is significantly wider compared to the other two elements. All right, and these are the contact points. So based on the controlling of emitter base collector junction, we are going to have significant changes in the current obtained at the receiver. So this leads to the second part, which we also have discussed, and that is with respect to PNP. We discuss it with respect to PNP. It's not that NPN will not be working in the same way. Same thing will happen for NPN as well. All right, except that here in case of PNP, the maximum current or the majority carrier is hole, whereas for NPN analysis, it will be majority will be electrons. That's it. So over here, that same thing I have mentioned, IE current is formed, and how it is formed, that is being discussed. So this is the junction where the IE is formed, and we are focusing on. Whereas in the next slide, we have discussed about the 2.5% of almost approximately a very small percentage of recombination that happens with the minority carriers of holes along and the electrons. And naturally, the lesser the width, the better is the chance that most of the electrons which are generated from emitter will go to collector regions. So that was what was discussed. Correct. So this is where I think we had ended our discussion. Now let us quickly discuss on a little bit of on that on continuing on that IE and IB, the different ways in which we are going to represent this parameters. All right. So please keep a note of this with respect to the transistor action. So if you observe the emitter current, the IE, which we have discussed, IE is equal to IB plus IC. This can be mentioned in another way, and that is given by IPE plus IN. All right. Now you can observe that why it is like this. Okay. IE is the same, whereas this base part or the base current that we are talking about, if it is an NPN transistor, suppose, then in the process, what is happening that it is a concentration of PE. This how we are representing over here is actually an NPN representation. Why? Because this PE represents a hole, the minority hole current, and this one is basically the majority hole current. Okay, a majority electron current. So that's why INE. So this happens to be IPE is almost representing an IB, and INE actually representing the IC. So that's another way of, if you have the concentration of your electron and hole, remember you can find out what is the total amount of current for that particular semiconductor. We have discussed this in diode where the concentrations were given. From that we can find out what is the current conductivity, what is the threshold, what is the overall concentration, what is the total current which is flowing to the diode. So those things we can calculate easily. So the same thing applies over here. So that's one of the relationships. And naturally, as I said, the IPE, okay, IPE is greater than, okay, I think this is in terms of PNP only, because IPE is greater than, far greater than INE, means the holes are the majority. So this is collector current we are looking at. IPE is basically the collector current because this is PNP. See this is PNP. So IPE is basically the majority current and INE is the minority electron. All right. So that is why it is shown. So holes current, if it is a PNP, naturally my hole current will be greater than the electron current. So that is what been shown over here. So approximately IE, okay, ideally is almost equivalent to whatever the hole current is, because the base is very small. Naturally, my INE, that is the minority current, also should be very small. But you will soon find that that will not be the case. Naturally, with realistic scenario, there will be some amount of leakage current that will exist. All right, so this is my IE. If you observe, same way the base current, as I already had told you. So IB is nothing but the total current IPE, that is the majority current, okay, minus IPC. IPE minus IPC. So the emitter whole emitter current minus the collector emitter current. Basically, this is my IE, IPE if you observe, okay, or capital E if you call it, and this is IPC. So IPE minus IPC is given by whatever you call, whatever you get it over here. Because naturally IPE will be greater. IPE greater because that is where the source, it is basically the source, the emitter is there. Right? So IPE will be greater than, at least some amount of greater than IPC. Okay, because by the time IPC is generated, remember there is some amount of recombination is happening. So definitely IPC should be less than IPE. The collector current will be less than IEE. Definitely. So that recombination part is basically what the IB stands. Right? So clear, everyone, this is how we are doing it for a PNP. NPN also the same thing will happen, except the sign will change. For NPN, what will happen? This will be INE minus INC. That's it, nothing else. Okay, just remember which one is the majority, which one is the minority. Whole thing will be clear. So IE, IB is this is the meaning of it, and the collector current can easily be find out IC, which is a combination of IPC plus ICBO. This is I was talking about. So IC, the collector current, is actually a combination of the majority carrier current, which is there over here, plus some amount of leakage current. So this is called as a reverse saturation current. Leakage current. Why it is leakage current? Because there is a reverse biasing present over here. Okay. And that's why if you remember in diode also we have discussed that whenever there is a reverse, whenever we have a reverse bias, definitely there will be a reverse saturation current that will also take. Remember the graph I told you. Suppose I have a graph like this. For a reverse bias connection, the graph was something like this. Some current like this. So there was some small current which was coming, and then after that, after a certain breakdown voltage, it was going very fast. So that small little current that we are looking at, that is ICBO. Okay, so if for the collector also the same thing will happen. So IPC is the majority current, that is primarily the source of the current, and ICBO is basically a lost current. You can say it's a leakage current that we are discussing with respect to the combination that we are in. So this is about the individual currents, how they are expressed in terms of different individual currents in emitter, base, and collector region. Alright, so but even you will soon find that all these individual calculations or the nomenclatures will not be that relevant, because we are mostly focused, or we are mostly going to consider this I equal to IB plus IC for our most of our calculations. But this is more detailed. Like, and if you go into the detail, if you are looking at the emitter itself, what will you observe? Like, so what if you are inside the base region, what we are going to observe? What amount of current that is passing through? If you're looking at the collector, what is the nature of current? So that is being given over in this particular slide. Any doubt with anyone? This is just the representation of emitter, collector, and base current with respect to the different other current components which are generated either in the emitter or the collector region. All right, but this is not the end. This is just a part of it. Since we have discussed about the three currents, this is how the expressions have hold. Okay, as per the operation. Now, based on the, so hopefully there is no confusion in the previous one. Is it fine, everyone? Previous slide.
Yes, sir.
Okay, let it be. I found a yes, so hopefully that is understandable. And later on, when the course material is there, you can also look into it. Now, the ideally, what happens, you can see that there are three portions of a transistor: emitter, base, and collector. And the connectivity also depends on these three possible region only. So one is called as, there are three possible combinations. One is called as the common base mode. The other one is called common emitter mode, and another one is called as common collector. So in general, from the term itself, is quite obvious that for common base mode or CB mode, the base of the emitter should be grounded. So if you observe carefully, this first diagram over here, this diagram, if you observe that the base is provided somewhere over here. Now, as it stands right now, the base is connected to the ground. Okay, that's a common ground. All right. And the output you are observing across the CB junction, VCB junction. Each of this configuration has its own advantage, share of advantage. One will be used for switching purpose, one will be used for amplifying purpose, right? That there are different ways of application by which this categorization has been made. That's why you can see three types of configuration based on the operations. All right, so we'll see the operation specifically later on after Cat 1 maybe, but these are the specific, these are the only three possible combinations of a transistor. You can see here in the common base, the base is common, whereas in case of here, if you observe, the emitter is common. So here it is a common emitter. See the emitter over here, the emitter is made common. Whereas over here, you can observe that the overall structure, whatever it is, the collector is over here. All right, and the collector is common. So this is common collector. So this is my common collector combination. This is my common emitter combination, and this is my common base combination. Right? So each, as I said, each one of them has its own share of advantages and disadvantages also. We will discuss that later on. We'll do that. But at least we will touch upon a specific few parameters, three parameters if time permits. We will discuss that, or at least the two parameters which are absolutely essential to understanding this configuration. All right. So the first thing is common base. Okay, common base configuration. Now, as I already have mentioned, that base terminal is grounded. The diagram itself is suggested over here. The base terminal is grounded. Okay, there should have been a ground connection over here somewhere. It's missing in the diagram, but it is basically something like this. It's like this. Okay, so the base terminal is common and it's grounded. So that's being mentioned. Now, the emitter based junction is forward biased and the collector based junction is reverse biased. Now, this is common to any configuration because this is the only way a transistor can operate. Right, so that is done. But the important part is base terminal is grounded. That's important. Now, based on this, one of the first parameter that comes in very handy and that is being discussed is called as the current gain. Please make a note of this. All right, this is called as current gain of a transistor. But the current gain of a transistor not only for general purpose. This is current gain of a transistor when the base is made common. So it is a when it is at CB configuration. So when it is at CB configuration, the current gain of a transistor is called as IC by IE. Why? Why this is current gain? Because you can see the collector current is basically the output and the emitter current is basically the input. So it's basically a ratio between output to input. Okay. So if you just generic way, if you observe, this part can also be called as forward current transfer ratio. Forward means because the IC is basically the collector, as if the current is flowing towards the collector. And current is natural because it's I we are considering, and transfer ratio is like from emitter to collector, how much it is going to get transferred. Clear? So that is being given by alpha. This parameter, please make a note of. We will see that soon that there will be another parameter of current gain in common emitter as well. And we will try to relate between that two parameters together so that we can alternatively use the different configuration at times. All right. So if you observe here carefully that we have the higher value of alpha is better as the transistor IC will be close to I. Remember, I told you over here in one of the diagram over here that if IPE is far greater than INE, we can approximate that IE is equal to IPE. What was IPE? IPE was the emitter current. Okay, the emitter current. So it's almost equivalent, we are saying, if this condition exists. Same way, if you observe here that if alpha is very, very high, it is more like high. Okay, it usually the value is between 1. Okay, maximally it can be up to 1. So if it is 1, then IC is equal to I. See here for yourself. If alpha is equal to 1, if alpha equals to 1, then we are getting IE is equal to IC, which is ideally the authentic ideal case that there is no such dissipation across IB and the IB is 0. That should be the case. So the more it goes closer to 1, the better is the replication of IE to IC. Correct? So this is about the alpha part. We'll see more. And then if I substitute over here, you can see that this equation we have already discussed. IC is equal to IPC plus ICPU. See here. This one. IC, the last equation. IC is equal to IPC plus ICPU. So that equation, if you substitute, okay, this IPC. So IPC can be replicated by in terms of alpha because IC is alpha into IE. So that we are substituting over here. So a relationship which was IC and entirely dependent on the collector current now has been related by an emitter current as well. So if I know that how much of is the leakage current, the ICBO, that is this one, if I know that, and if I know that this is the transistor where the emitter current is this much, and we are specifying an alpha which will magnify the current to certain extent, then we can find out what is the expected collector current at the output. So you can see in this particular example, as I said already, I think I have already mentioned this, that the value of alpha is always less than unity because IC will always be less than IE. As I said, this condition IE equal to IC is a hypothetical value. It will never be, but will definitely what will happen that IE will definitely be greater than IC, because IE is a source, remember, and IC is a collector. So definitely there is a change, i.e. the amount of current which is generated by the electrons will, if even if we consider a very small portion of the current or the emit or the of the electrons are combining with the holes, even if we consider that, but still there will be small little leakage current, even if you are considering that. And as the leakage current will be there, definitely there will be drop in the collector current also. So that is why this condition will always be true of IC less than C. So suppose you are calculating a numerical and you come across that a condition where you get IC greater than IE, which will never happen. So somewhere you have made a mistake. That's a like a tricky question at times. So this is about it. Now let's solve a small little question on this. For example, in a CB configuration, the IC, the collector current, is given by 4.10 milliamps. Right? The emitter current is given by 5.18 milliamps. So we know IE, we know IC. Calculate what is the estimated IV. Okay, the base current is there. So if you observe carefully that in this case, we can easily find out what is alpha. Why? Because we can take the ratio of it. We can take ratio of alpha as IC by IE. That means IC is 0.410 divided by 5.18 milliamps. Okay, so this is how it is mentioned. Now, if you go about it, you will get the alpha value of 0.715. Now, the question is to find IB. Okay, now how do I find IB? Okay, it's a very simple equation, because you can see this equation is again being used. I told you this IE equals to IB plus IC is the core equation we are going to use. So IB will be nothing but IE minus IC. Okay, IE minus IC. Now IB minus IC, if you observe over here, okay, so that IC is nothing but alpha IE. We have to consider that alpha IE. So we substitute everything and we get the final answer as 1.08. Okay, so this is about how we are going to evaluate with respect to the configuration of CB configuration and the current gain. So this is a parameter. This is a parameter given for the particular value for the particular transistor. All right. So that is more likely. All right. Even you can observe that if you just give me a moment. Suppose you have this 5.18 5.18 is the emitter current, and we have 4.10 as the collector current. All right, so that eventually we have to include the magnifying factor over here, the current gain factor over here, in order to solve the final answer. If you are not doing that, you are making a mistake. You have to include the alpha element to the equation. All right. Otherwise, you will have a different set of results, which is not correct, because you are not including the alpha factor. This current gain factor will definitely be there for a common base configuration. Okay. Ideally, for a like suppose the connection we are not making in that way, then you can say that IE equal to IB plus IC, and we can substitute directly and we can get the answer. But the problem is, for any such configuration, like here it's mentioned as CB configuration, you have to include alpha in your equation. Okay, so that is where we are getting the final answer. All right, so this is about the common base alpha. In the same manner, we have another current gain, but this is in terms of common emitter. As I said, they are very common, so nothing is new. Here, what is happening? The emitter is made common. Okay, so if I go back to the circuit once again, so your common emitter was here. So your emitter is being made common. All right. So the output, if you observe output current, we are measuring over this pane. All right. So what will be the nature? So you can observe the input over here is IB. You can go back to the diagram. Your input is IB. What is your output? Your output is IC. So you go back. Sorry. So your output is IC. So again, the same rule applies. So the based on the circuit, the input is this and the output is this. So again, we take the ratio of output current to input current and we get the current gain under a common emitter configuration. So that's the only catch. If it is a common base configuration, you have to choose alpha. If it is a common emitter configuration, you have to choose beta. Okay. And if you observe carefully, same way, IB into beta, if you consider over here, that will be equal to IC. So for a common emitter configuration, your IC will look something like beta IB. It's a factor. It's a factor that is given. All right. So in that same manner, you can observe that beta for a common emitter, the current gain is in the typical range of 200 to 300. Please make a note of it. It's entirely different to that of alpha as per the value. Remember, in alpha, the maximum value was 1. Okay. Here, the value can vary between 20 to 30, 20 to 300. So you can observe the more the better, the higher the value of alpha, rather beta, we will get a better system, because the more the value of beta, it means the IC will be more. And that's what we want, the collector current will be. All right. So that is how it is. So if you observe here, IE, the same equation can be rearranged again. So IE is equal to IB plus IC. All right. And in that, we can take some ratio, like we can take divide by IC. So we get IE by IC equals to IB plus IC. This is relating alpha to beta. Okay, the two parameters that we have. So IE by IC is equal to IB plus IC plus 1. Now IE by IC is nothing but 1 by alpha. Remember, we had just now found out over here. So this is 1 by alpha is equal to 1 by beta plus 1. Hence, we can say that alpha, we can say that alpha is given by, please make a note of this, alpha is given by beta by 1 plus beta. Please make a note of this. This is a relation between alpha and. So the two current gain factor from one configuration to another, we can relate it in this way. Or on the other hand, you can say beta is equal to alpha by 1 minus alpha. So any given question, if alpha is provided, you can find out beta. If beta is provided, you can find out alpha. Correct? So this is about the two parameters for common base and common emitter. Naturally, we can also have another configuration, common collector. And for common collector also, we will have a current gain parameter, and that is given by gamma. But it is not that important, so I've just kept it that way. It is, again, you can see the diagram here for common emitter, a common collector. The input over here is IB and output is IE. So the relationship is IE by IE. So again, that based on what your configuration is, how you have configured your circuit, you are getting the results. So this is gamma, and gamma can also be related to alpha and beta also in the same manner. But I'm not going into that. I'm not going into that detail for the time being. You can actually see one of this question for your because we'll wind up the session and we'll see that how things goes. Okay, now it's 2:40 almost. So you can see the question is something like this: the value of beta for transistor is 100. Okay, value of beta is 100. Now IE is given by 10 amps, 10 milliamps. So emitter current is given. What is estimated IB and IC? Right? Now, in this particular case, since beta is provided to us, okay, since beta is provided to us, we can directly find out what is alpha also. So we can say alpha is like this. Okay, same equation, beta by 1 plus beta like that. Now we have ample equations where we can substitute. So suppose, for example, I want to find IC. IC will be nothing but alpha into IE. IE is provided, put the alpha, get the answer. Simple. But remember to include alpha and beta in your calculation. That's the only thing, only catch. Same way, IB can also be calculated using IE minus alpha IE. The relationship just now we had explained over here. Okay, over here, IE minus alpha IE. The same question we are doing again. So alpha IE and substituting everything, we are getting around 0.2 milliamps. So you can observe that for a IE, which is 10 milliamps, okay, for a conventional system where IE is 10 milliamps, given the condition, IC is giving around 9.8. So it's very close. That is very close. But you can observe the condition is satisfied. That is, IC is less than IE. And you can also observe that IB is significantly small compared to the rest of the current. So that is also proved. All right. Similarly, in the course material, you will find these two questions also. In the same manner, you can actually solve them. Same manner. For example, check the figure, determine the value of IE. I think it's IC. Okay. Because IE is given already. So IC and IB given, IE is this and beta is this. Same question. So this is an NPN configuration. We can find out easily that what are the equations. Same way, just like we have solved over here. Same way you can find it out. So this kind of questions you can expect even as we were leading towards. This also you can expect out of the module that we have discussed. All right, so we'll stop for the time being with respect to the module, to be honest, because I know I won't be going further. So let me just stop this. Okay, and let me come back. Stop sharing as well. Okay, so I'll just stop recording for the time being so that